Welcome. I hope you are all enjoying reInvent so far. Incredibly excited to have you in this session today. So just by a show of hands, I just want to ask a question. How many of you would say building embedded systems is really hard work? No matter what industry you're in, whether it's industrial, connected cars, wearables, or smart home, or any other IoT vertical, your embedded systems have to do many things at the same time. They have to deal with external events, be in ambiguous situations without human interaction. Then they have other components like managing power consumption. And then on top of that, you need to get them connected to the internet. So as a customer, as you're building your IoT backends and your IoT applications, you feel like you're on a Starship Enterprise. The internet, your IoT applications, the final frontier, boldly going where no one else has gone before. My name is Wally Oladihin, and I'm a solutions architect at AWS, and I help customers on their cloud journey. And connecting your devices and using AWS IoT and serverless technologies is just as fun as getting down on the dance floor. So what about you? If you're in this session, I assume you know about AWS IoT and the serverless technologies like Lambda and API Gateway. But I also assume you know about the other services around this ecosystem, like DynamoDB or Elasticsearch. And what will you learn in this session? We'll talk about the benefits of serverless IoT backends. Then we'll dive into the building blocks. How can you start actually building your applications using serverless technology in your IoT ecosystem? And then we have the pleasure of having iRobot speak about their customer experience and their use cases around IoT and AWS. So we have to start with the advantages of serverless in your IoT backends. And to understand how serverless can really help you build your applications, we have to start with the principles of IoT architectures in general. So many times you get started building your infrastructure, you're thinking about certain concepts like being anti-fragile or DevOps or microservices. And these are important for your IoT architecture, but these are really byproducts of some more higher level principles around fault tolerance, visibility, or agility. So you want to see your system and imagine a scenario where your developers can deploy new business logic without impacting your end devices. That your operations team has visibility into every single event that enters your IoT backend, all the way through until it lands into your data warehouse or your data lake. And you want to underpin that with security from the time the device connects all the way up and through the cloud. So what are the advantages of using serverless to reach these principles and really design these characteristics in your IoT application? When you think about serverless, it's first about scalability. With AWS Lambda or API Gateway, we scale the number of invocations, or we scale as you make more API calls. So this removes the undifferentiated heavy lifting of managing the infrastructure as you add more and more devices to your fleet. With serverless technologies, you don't pay for idle. So you don't pay until you actually invoke your Lambda function or make an API request to API Gateway. But there's other advantages of using serverless technologies with IoT. From an architecture perspective, since these services are stateless, you have to start thinking about how you want to scale your application from day one. And with IoT-centric data and IoT-centric ecosystems, we all want to strive for event-driven architectures. All of your telemetry are events, all of your telecommands are also events. And by leveraging serverless technologies, you start thinking in this mode of, how do I take an event, process it, and then send it somewhere else? So now that we know the advantages, how can we start working with the building blocks? How can we create a blueprint of what services to use and why we should use them? So with our serverless IoT backends, we have our foundations, AWS IoT, AWS Lambda or API Gateway. The first building block is around state management. This is, what are you going to store? how are you going to store it, and most importantly, why do you store that data? The next building block in your serverless IoT backends will be the fast pipeline. We talked about agility. How can we decouple all of this ingestion and requests we're getting from our devices from our backend business logic? And our fast pipelines can help us do that. And the last building block in serverless IoT backends is all around operations. We need to be able to deploy our functions as a unit and as a group in a repeatable fashion. We also need to have insight into how our application is actually performing. Do we need to do some troubleshooting? Do we need to take something offline? So operations becomes a core part of how you design and build your IoT infrastructure on AWS. So with these three building blocks, you can create this rich and robust ecosystem where your application is fault tolerant, scalable, highly durable, and you have visibility inside your ecosystem into all the messages you're receiving from your devices. So how about we use an example to dive in a little bit deeper, to take those building blocks and actually build some solutions and build an IoT backend using serverless technologies. For our example, we'll use smart transportation. So I live in Boston, so I take the subway, but you might do commuter rails, or you might take a different train. So for our application, we'll have our train or subway publishing telemetry about its geolocation. Where am I on a given trip? We'll have two other things or devices in our ecosystem for this example. We'll have our mobile app, so our commuters can take out their phone, they can say, here I am on my current journey, and then we can also do things like send offline push notifications. And then we'll have our turnstiles, where you enter and leave a given station. And for our example, this will be sending up, how much foot traffic are we seeing for a given station on this train line. So to take this example and start using the building blocks and show how we can architect these fault-tolerant solutions using serverless IoT backends, we'll first tackle state management. And when you think about serverless, you immediately jump to that first advantage that I told you about serverless being stateless. But just because it's stateless, it doesn't mean that your state doesn't matter. It's actually even more important to think about how you want to manage your state. And that falls in two categories. The first category is managing and storing your output. So your Lambda function will run, it will receive an event, it will take in additional context, and then produce an output. And then you'll store that in some technology. It can be a search index with Elasticsearch, or you want to do time series with Dynamo, or you want to use Lambda VPC and store it in an RDS instance. But view that output as a moment in time. It's your current state of your device or of your ecosystem. But there's a second type of state that's important in serverless IoT backends. And that state is the individual event itself. So you want to store your output. You've run a calculation and you've put it somewhere. You also want to store the event that triggers that output. So in the example of our smart transportation, we might have the full line that our train is riding on. And every single current moment we can say, here's what a train is, it's at stop 1 or stop 2 or stop 3, and that's our output. Well, what happens if you want to go back in time to say, how long did it take my train last week? By storing each individual event, your input, you can create arbitrary projections on your data. So you have your current time, which you're storing your output. What does my system look like today? But by storing each individual event, you can go back in time. You can do inspection. You can have a true audit log of your data. So with state, we think about both aspects. How do you want to store the output, and how do you want to store each event? So let's apply this to our smart transportation. We talked about our train and its journey. Now we'll talk about the mobile device and getting it onboarded. So we'll use API Gateway and Lambda. And instead of just storing a calculation of a user and information about his profile, we'll actually just store a sign-up event. This allows us to, again, look at these events later on and actually see how a user's onboarded. So how do we get our output? We'll use DynamoDB streams and use another Lambda function. This Lambda function is responsible for creating a thing in AWS IoT, giving it permissions or policies, and really onboarding the device so it can connect to AWS IoT directly. We'll then have a second Lambda function that onboards a user for offline SNS. So in our example, we said we want to give users background pushes because I may not have my phone on when I'm at work. I might say, I'm not commuting anymore. But I still want to send this end user information about maintenance, or maybe a specific line is down, you should take an alternate route. So we'll store a different type of output, and that's an SNS. We do some other interesting things with state by leveraging the republish rules in the rules engine. So let's say for our devices, we want to know which subway lines or train lines are you really interested in. I might take a red line and then switch to a green line. I might take the commuter rail one day, and another day I might drive. So when I open up my app, it'll list everything that I've subscribed to using the AWS IoT lifecycle events. And I can directly republish that information onto my IoT shadow. So now I have current state. Using the shadow, I can say, which lines is this given device listening to? And going back to our principles, just applying Lambda, using DynamoDB streams and API gateway, we're able to achieve some of these high-level principles that we wanted to get to. We have a fault-tolerant application. Lambda will retry and scale on your behalf. It's cost-efficient because you're only paying when your Lambda functions and your API requests are being triggered. And we have security from the time the device connects over, let's say, MQTT or WebSockets through sending it in Lambda via IAM roles. So when you use serverless IoT backends, you're going to be leveraging Lambda in different ways, but you're also going to be leveraging the rules engine and republishing and subscribing in different ways as well. Let's just show an example of what these rules might look like. So we talked about our users subscribing to different parts of their journey, parts of their train stops. So in our rule, we'll actually select the topics from our lifecycle events for subscriptions. And we'll create a new command. We're transforming our data to say, store this current state directly into this given device. The next building block is your fast pipelines. So as your IoT ecosystem grows, it's going to be harder and harder to really keep kind of consistent data. So you want to look at ways of eventually creating eventually consistent data, where you can start processing things in batch or over time. So a fast pipeline is made of three components. You have your producer. This will be your rules, your Lambda functions, or an API call through API gateway. You have your pipeline itself. Those are going to be Kinesis, SQS, SNS. And you have your consumer. This will be AWS Lambda, or you might have an internal application that wants to pull this information off as well. When it comes to your pipeline, you have many choices for really queuing and then pulling events off of the system. Use Kinesis if you want to do aggregation. If you want to say, I want to look at 100 or 1,000 events at a given time, Kinesis can do that batching and pull them off in one unit. Use SQS for doing distributed transactions. I want to process this message just once. And once a consumer does it, it should delete it. And then SNS can provide broadcast patterns. And S3 is where you store intermediary binary or data that you then want to invoke another Lambda function to process. So when should you use a fast pipeline? So we talked about transforming your data and sending it in your serverless IoT backend. You can do that through a republish rule that we showed earlier. You can do that by directly invoking a Lambda function from your IoT rules engine. Or you can do that through the pipeline. Look at using pipelines when you have high or unpredictable workloads. Even though we scale Lambda for you, there's a number of concurrent requests you can have at a given time. So you expect you to have these very bursty workloads. Use Kinesis to provide that buffer for you, or SQS, or S3. Also use it for doing event analysis and aggregations. So instead of looking at just one event, you want to look at 10 or 20 or 100. So let's use fast pipelines in our application. We have our turnstiles communicating with our mobile device over the local network. It's going to publish on a turnstile information about traffic for this given stop and this given train. We'll create a pipeline by using Kinesis, but in this case, Kinesis Firehose. And in Kinesis Firehose can write directly to Elasticsearch. I'm not managing any of the infrastructure. Kinesis is batching it for me and then doing a push into Elasticsearch. We can also then write that to S3. this becomes another start for a pipeline. We can kick off a second job from this information. We have our devices. Remember, we're tracking users as they start their commute and end their commute. So the mobile phone will send updates about where a user is on their trip. We still want to store all of these individual events, but since we know they're bursty, they're highly unpredictable, in this case, we use Kinesis streams. And that will listen to all of the events that are coming from the turnstile, as well as all of the events coming from a mobile phone. And now we can aggregate using Lambda and then storing this again in DynamoDB, giving us essentially history and events of the commuter and the subway. We also talk about offline. I want to do SNS push notifications when my phone's not connected. So we can have a last will and testament disconnect message that we'll listen to and then put on to SQS. Then we can delay this. We know that as you travel throughout the day, maybe your phone cuts in and out because you're going underneath the tunnel. So we use SQS to do this as a transaction, but also delay the final execution. And using Lambda, we can get some interesting patterns where we can pull this off of SQS with one Lambda function, and then have the second Lambda function actually process and do a lot of the heavy lifting. And then have a final place for storing our output. So with this type of architecture, we've added more moving components, we're using more Lambda function, we're using pipelines, and we're able to achieve the fault tolerance, cost efficiency, but now we also have additional agility. We can take these functions offline and still process data. We can still have it sit there until we're ready to take action on it. So our last building block is around IoT operations. When we think about IoT operations, we have to think about logging in metrics inside of our system. And it'll be different when you're using serverless technologies. Because these are all running Lambda, to get the same consistent view of what metrics you're publishing and what logs you have, you should have a shared library in your Lambda functions that say, here's the output we want for storing logs, here's how you actually write metrics. So you're unifying all these Lambda functions under one stack and format. You should enable the AWS IoT CloudWatch logs. You can listen to these logs and then make recommendations about what to do next. From a deployment perspective, you use AWS CloudFormation, but then you'll be grouping all your individual functions as services. And now that you have CloudFormation, you're treating it as infrastructure as code for a service, and you're listening to all the logs and metrics and correlating them with individual applications, you're able to create more fault tolerance. You can then say, if my Lambda function starts to error out listening to Kinesis, stop that function from running so I can do an analysis, and then send an alarm to my operations team just so they can look at, did I just deploy new code? Is it timing out for a different reason? Because you can deploy really quickly, and now you have more metrics coming through using CloudWatch logs and metrics, you can really drive some graceful degradation modes and other modes of really actioning on your request. So let's add that to our smart transportation. We want to listen to how our rules are performing because it has application logic. So we'll actually use Kinesis. We use a fast pipeline. Hook that up to Lambda, and now we can write a unified log of, is this rule functioning correctly? Am I seeing output that I'm expecting? We're going to have for our Lambda function a shared library that says, here's how you write to the specific logs in a specific format, and here's how you write your metrics. So we can also trigger alarms off of that. And by doing this, we add visibility to our architecture. So when you look at the rules engine, that example of publishing how your rule is interacting for a given event, your rules will look a little bit different. You won't just have the payload with the select start. You'll have things like the new UUID or a trace ID, so you can track this individual request. You'll have a timestamp. When did I actually see this hit the broker and hit AWS IoT? Then you'll also pull context off of the MQTT topic itself. So I want the ID of the subway or the station. And we talked about the agility aspect, using our functions as code. So you wrap your CloudFormation templates, you wrap your Lambda functions as units in CloudFormation. So all of these templates you can deploy independently one team can own not just the rules, but the entire pipeline from when a message hits the IoT system all the way through your backend. And even though they're separate units, you'll have times where your Lambda function will need to actually communicate with another service. And so you can either share data directly via Lambda functions, or have an interface with API Gateway, or an internal interface with another Lambda function. So in our smart transportation example, we just used these 3 building blocks. We figured out why we needed to store data or process it, or how we wanted to process it. And then we moved it to the system of how fast do we get it? Should we use a pipeline or not use a pipeline? And then we covered how you can add more context so you can do operations. I now have the pleasure of introducing iRobot so they can talk more about their use cases and journey to the cloud.
Thanks, Wally. Hi, I'm Ben Kehoe. I'm a cloud robotics research scientist at iRobot, and I like to be outside. So we're iRobot. We are the consumer robot company. We make the Roomba, which you may be familiar with, and occasionally serves as intelligent transportation for cats. We also make the Brava Jet, which is a floor mopping robot. But we're not a floor care company, right? We're a robot company. We've been around for 25 years, and we have a history of working in many different areas in robotics. But beyond that, we're also a smart home company. We believe that robots can provide a unique benefit to the smart home in that as mobile sensing and actuation platforms, they build and maintain maps of the home over time, and that can provide value to, through its spatial context to other smart home devices. However, we have a long way to go to achieve that smart home dream where you just live your life and the house does the right thing, right? You buy a new bulb, you screw it in, the house picks up that there's a new bulb there, configures it, integrates it with your existing scenes, and then over time adapts to your preferences, right? You may have a voice user interface where you're communicating with it and saying, I didn't like that much, and it learns from you. And as the seasons change and your preferences change, it will change with you. But to get there, we have a foundational milestone in our Roomba 900 series, which is both connected and systematically navigate, so it builds maps. And so in the little over a year since we've released this, mapped nearly 1 billion square feet, and we think that this will enable us to start providing those smart home user experiences that we want users to have. So now, understanding what that means for us, if you're in IoT, your users pay for your device once, right? They buy it at the store and they take it home and they connect it to the cloud, and then you have to pay the cloud cost for the life of that device. And what that means is that the better that the mechanical and electrical engineers do their jobs, the more the cloud costs the company. And so if you have a subscription model, right, or a freemium model, you can get recurring revenue that will offset some of those costs. But if you don't, or if your freemium model is that you have, a wide user base that's not subscribing, you want to minimize your cloud costs as much as possible. And that drives a lot of our architectural decisions. So why did we choose serverless at iRobot? We have experience building devices, not cloud applications. The Roomba predates AWS by 4 years. And our fleet is already at scale. We sell, a lot of robots. And so while only our top of the line is currently connected, that's going to roll out through our product line, in the near future. And so we have this tidal wave of connected devices coming, and we know that it's coming. We know what the scale it's going to be, and so we have to build a cloud system that will meet that demand. With serverless, that allowed us to skip the undifferentiated heavy lifting step. We didn't have to learn how to provision and scale traditional architectures as part of scaling up. We were able to skip that step and say, we don't want to manage that. We'll have AWS do it, and we will just write business logic. So the architecture then, what does it look like? We have some cloud-side features that we need to support that enable interaction between our app and the robot, as well as enabling analytics for us. And to support those features, we use a lot of AWS services. 20 plus. I don't think we're quite at 50% of available services yet. It went down again with the keynote today. But it's quite a number, and you'll notice that there is no EC2 up there. We don't use any bare EC2 instances. We use Elasticsearch and Redshift, which both have managed instances that are kind of hidden from you. So that's sort of on the serverless spectrum, in my opinion. But what does it look like, right? So before serverless architecture, you're writing some code that goes on EC2. And you've got functions that are interacting with each other, and you're storing that in some state, or maybe you've got a database that's sort of nearby in the same subnet, something like that. And when you go to serverless architecture, you're exploding that, right? You're taking each of those functions and wrapping it in an individual Lambda function, and you're moving that state out to DynamoDB. And one of the results there, right, is that in some of these functions, all you're doing is making SDK calls. And those SDK calls are more complicated than the original local calls that you were making, right? You have way more error conditions to handle. Your happy path is still the same, but you're dealing with a lot more different pieces. And when you actually get to what a real service might look like, this is just one flow in our system where to register a robot, right, sending something up to API Gateway, it's checking that certificate, putting it on a queue so that we can make sure that these robots absolutely get registered when they talk, that we don't drop that on the floor if something's wrong. We're reading off that queue, and then we're talking to the shadows, and we're setting up permissions and emitting lifecycle events and logging all of this, right? And this looks really complicated. But if you think about all the things that you would need to do if you were building this as a monolith, all of those pieces would be in there, and your call diagram would look like this, right? And so the lesson is that when you go serverless, your call graph becomes your component graph. It moves into your infrastructure. And there's an important consequence of this, right? It ends up being that your infrastructure is more complicated, but it means that you're treating distributed systems thinking from the get-go, right? It moves from the boundaries where you think about, just sort of how a couple of these systems work with each other into, I need to think about this for every step of the process, right? Tools like Chaos Monkey exist to remind us that we're writing distributed systems code. With serverless, it's evident. You still need to be mindful of it and work hard to do it and do testing under degraded systems. But it's sort of more upfront and less hidden that that's what you're doing. And that's going to cause you to build robust by design systems, right? You're going to go with event-based strategies. You're going to go with CQRS that will allow you to handle these cases more readily. At the same time, a lot of people think that serverless and functions as a service mean microservices. But that's not really true, right? It's this component graph equals call graph idea, where if you look at your call graph in a traditional system and it's a very tightly coupled web, you're building a monolith. And if you look at your call graph and it's a bunch of little tiny webs that are interconnected by sparse connections, you're building microservices. The same is true of your infrastructure in serverless. If you build serverless infrastructure where all of your components are talking to each other, then you're building a monolith. And if you can separate that out into little pieces, then you're building microservices. Now, at the same time, it does naturally fit with microservices often, because you can wrap an individual Lambda function or a small group. But it also behooves us to ask, why do we actually choose these microservices in the first place? So for coding, right, it eases development because you're working on something that's easier to understand. It makes testing easier. It makes maintenance easier, right? All of this sort of reduces the scope that you have to keep in mind. It's also easier for deployment, right? You have smaller units of deployment, so it's easier to manage. And you get organizational benefits, right? If the teams are more decoupled, they can have fewer meetings. And you'll see in this talk, I use that sort of circle diagram to mean microservices a couple of times. If you have microservices, they need to communicate. And in traditional architectures, that's usually RPC, often HTTP, maybe gRPC, maybe a message bus. But when you're serverless, you kind of only have one option, which is HTTP over API Gateway. And you'll see that that's kind of like baked into the serverless framework and things like that. But it has implications, and I'd like to talk about that. So imagine, right, a permissions service where that maintains the permissions between a user and a device. And it's essentially at its core a database, right, that maintains those links. But suppose that it's not just a database, that it also contains some encrypted information. So you need KMS, which means you need some processing involved there too. And the typical answer is then, okay, well, we'll put a Lambda function in there, and we'll put API gateway in front of it, and then we'll use that. That works. And when you have a service that says, what has my device been doing for the past month, it needs to check, do you have permission to access that device? And so this Lambda that's going to return through, say, an API gateway call, some history of your device, has got to go into permissions and call that API gateway, which calls Lambda, which talks to KMS and DynamoDB. But that means you get extra latency, right? That API gateway adds some latency because you're actually going all the way back out to CloudFront. And then the Lambda behind it has some latency where it's doing that processing. And not only does the permissions Lambda cost you money while it's running, but the Lambda that's calling it, which is waiting, is also costing you money. In a traditional architecture with async I/O, you're able to, you spend basically no marginal cost on waiting for a high latency service. But in serverless architectures, that's not true. Now, if you're able to go very heavily event-based, where you can make asynchronous invocations, you can get around some of this. But if your entry point is API gateway from like your mobile client, as an example, then you essentially have to make all asynchronous calls behind it, and you run into this problem. So there is an alternative, and the alternative is directly accessing resources in another service. And your initial thought should be that you're horrified because how do you get separation of concerns here? And we address this by having SDKs defined for our services. And you can do this already, right? Even if you're going the typical route, API Gateway will generate SDKs for you. And those SDKs are thin wrappers around HTTP calls that will, they handle the SIGV4 authentication and things like that for you. But essentially, they're very thin wrappers. But what we do is we say the service can provide a thick SDK, a thick client that talks directly to KMS and DynamoDB. And then that's defined with, as an example, the permissions service. But when it gets deployed, it's bundled with the history service. And so the downside here, right, is that while it's well separated in the code, when you deploy, you get all this coupling. If you update the schema in the database, even though the API, which is still just, does this user have permission to this device? That SDK has to change, and so you have to redeploy all the callers. So you have highly decoupled deployments, which means while you've got microservices in code, you've got a monolith in deployment, right? So you get some of those microservice benefits, but not all of them. I'm going to argue that this is okay. For our use case, where we're driven by reducing cost, this is a good way of achieving that. But first, that monolith that we're deploying, how do we deploy it, right? So we'd like to not deploy in place. That's, at scale, a white knuckle experience. You got to just hope everything works. So you want to do some kind of phased rollout. And there's terminology for this that is kind of arbitrary. People use it to mean different things, so I'm just going to arbitrarily pick this. If you have blue-green, you're updating behind the load balancer, so your endpoint stays the same. The client sees no difference. And the workers, containers, whatever, change there. And this is essentially what API Gateway and Lambda do when you do an in-place update, is their load balancer stays the same, and their Lambda containers that are handling your requests are getting rolled out. But they don't provide that functionality to you. You can't choose how quickly to roll that out or start rolling it back before it's all done. On the other hand, what I'll call red-black, where you're standing up two copies, so two load balancers, two endpoints, with completely separate containers, workers, whatever you want to call it, behind, and then you're switching the client from one endpoint to the other. So we can do this on serverless. But normally, this is a little bit of the downside here is often, well, I don't want to set up a whole new system that's going to cost me a bunch of money. But we're not paying for idle with serverless architectures. So you can put it up there, and if no traffic's going to it, it doesn't cost you anything. So that's the route that we go. But then you ask, right, is this per service, or is this the whole system, right? Are you doing the entire application, all the services all together? And for us, because we have that highly coupled deployments, we do the latter. But again, you don't pay for idle, so standing up a new copy of the system is not any extra cost. And it's scalable in the number of services. You're setting all these services up in parallel, essentially. So there's not much overhead for setting up 100 services more than 10 services. It's not scalable in cadence. As you can imagine, if you've got V1 and you deploy V2 and you're switching clients over, and now you want to deploy V3, how the clients should be switched over to that new deployment is not very clear. So we stick with a fixed cadence, where if you want to have your teams very decoupled, where they can choose to deploy their own code at their leisure, this pattern isn't going to work. So now this brings up, how do you switch clients over, right? You've got a client that's talking to red.example.com, and you want them to move to black. And so you need some way of pushing them over. A traditional answer is DNS, where you've got a well-known domain, prod.example.com, that returns a CNAME to your deployment. And that pushes them there, and then you can update that for some percentage and send them over. Now there's some tricky issues with this anyway, with DNS clients. It's a little easier in IoT because often you control the entire network stack on your device. But there's other problems. CloudFront custom domains, which is how API gateway custom domains are implemented, you can't have the same custom domain on multiple CloudFront distributions or multiple APIs. So if you say prod.example.com is red.example.com, you can't say that a CNAME to prod.example.com will be able to route over to black. And I've seen some, the MyTalk group actually a couple days ago released a pattern that allows them to do this by sort of shuffling around domains, but it's definitely a workaround. And so we didn't take this route. Instead, we have a separate service where it's a well-known URL, service-discovery.example.com, and it returns a payload that says your host is red.example.com. And then that will change and move the client over. And there's a lot of benefits to this. We have multiple endpoints, right? We have API gateway and an MQTT endpoint for AWS IoT. We can keep the clients in sync for that. We have multi-region deployments that can move clients over transparently, whether it's a deployment within a region or moving robots between regions, right? You still have to deploy this service, right? And you can't just have service discovery all the way down. So you need some way of deploying that service. And for that, we use CloudFront. And so in this model, you're switching people over by updating the distribution config in CloudFront to have the origin go from red to black. And then you have a custom domain for that well-known domain sitting on your CloudFront. Now, API Gateway uses CloudFront, so you're putting CloudFront in front of CloudFront, which is a little wacky, but we get this benefit from the red-black switchover, and so we think that it's useful for that. You can also serve out static files along with that, and if they change during a deployment, you can switch the whole distribution config over, and your static files will be in sync with your API. So I want to switch gears here a little bit and talk about some patterns for AWS IoT. And so the first is how to do secure file transfer. So the problem is that you have a device and, say, an S3 bucket. And either you want to upload a file to there or you want to download a file from there. But your device doesn't have AWS credentials, right? It has a certificate that enables it to talk to AWS IoT, but it doesn't have a access key and secret key. But you don't want to leave that S3 bucket open to unauthenticated calls. So what you can do, you can access AWS IoT and ask for a way to get there. So you publish a request that says, I want to upload something. And it goes into a Lambda, and the Lambda talks to S3. And using the SDK, I mean, you can build these yourselves, but the SDK makes it easy. You can get a pre-signed URL. And these pre-signed URLs have credentials in the URL, in the query string, that are scoped just to the API call and the parameters that you specify, and only for a limited duration. So it helps you keep that very secure, and you can deliver that back down to the robot, and the robot just making a plain HTTPS call, right? You don't have to muck with the headers or anything. You can just send that right along to S3, either a get to download or a put to upload. But now suppose that you want to encrypt that object, right? And not server-side encryption. The distinction here is, you can check the box for server-side encryption on S3. And in my opinion, that gets you essentially just regulatory compliance. It protects against someone in AWS stealing a hard drive and inspecting what's on it. If they compromise your credentials or your permissions and they can access that bucket through the API, they get the plain text. So instead, you want to encrypt that object yourself when you put it in there so that if they have access to your bucket, they still can't use the data that's in it. So you want to have that encrypted in a way that the cloud can understand and the robot can understand. But they don't share any secrets, at least not initially. So KMS will give you a symmetric encryption key. And you want to use symmetric encryption because it's faster than asymmetric. And this is what the cloud will use to decrypt the objects in S3. But you don't want to just send that down plainly to the robot, because if anyone's listening into that connection, they get your symmetric key, and then they can see all the data that's in your S3 bucket. Luckily, the public key is on the certificate, which is stored in AWS IoT. So you have a way, just out of having registered your device with AWS IoT, to encrypt information in a way that only your device can decrypt it. And you send that back down to the device, which then decrypts the symmetric key with its private key, and then you can make that transfer. Either it encrypts it and uploads, or downloads it and decrypts. So continuing a little bit on security, but moving into certificates more specifically, a huge benefit that I don't think gets talked about enough is bring your own certificate authority certificate. So we have once, before going live, transferred our certificate authority cert onto AWS IoT. Beyond that, we do not involve AWS in our manufacturing process at all. And this is something that's very uncommon in IoT cloud providers. They want to provision your device identities, and AWS will happily do that for you. You can download certs, generate them on IoT, and download them, and this is all good. But what that means then is that you have to secure that download process. Then you have to transfer those, and if you're manufacturing in China, you're going across the Great Firewall, and then getting that onto your assembly line and into your devices. And that's not only a very long logistics chain to secure, it also means that if it's held up anywhere for any reason, that can hold up your production line, which is just not acceptable. So instead, we can provision those identities, those key pairs and certificates entirely within the factory, right? They don't leave, they never go. That private key is completely secret all the time. And then we sign their certificates with our certificate authority. And we keep those device certs and stuff around, but we don't send it to IoT. We don't send it to AWS at all. Now, when that robot, however many months later after it, sits in a store on a shelf and somebody buys it and they take it home, they wrap it, and then it comes out at Christmas, whatever, talks to IoT. We launched or designed this before just-in-time registration was available, and so we go through API Gateway to do this. So it's sending up that certificate, and a Lambda is going to look and put that on IoT. And IoT is going to look and say, this is signed by the correct CA that I have registered, and I'm going to let them make an authenticated connection. And it's hard to understate how important this is, because it means that even if you have existing devices that you've put on, that you've signed with a CA that you own, you can connect those existing devices to AWS IoT without having to collect their certificates all again. Certificates on IoT have some implications for account structure. First, the shadow and the topics aren't namespaced. So this means that if you put multiple developers into the same account, you should already have separate prod and staging accounts. That's just good practice. But say you had one dev account. You put everybody in there. A developer accidentally starts listening on the root topic. They're going to get everybody's traffic, and they're going to be really confused. Or they start publishing on the wrong topic, and then somebody else gets crosstalk. Right? They're going to step on each other's toes. For testing, right, you want to purge the registry so it starts clean. But because everybody's in there, you can't just wipe the entire registry. You have to go through and pick out the ones that you want to remove. So it gets tricky. So we take the route of every developer, every test server gets its own account. And when I made this, I said, well, after 10 accounts, it gets a little easier to get a process going. And I'm very excited for AWS organizations to make this even easier. So I would recommend going with multiple accounts. However, certificates in AWS IoT must be unique in a region, even across accounts. So a certificate is in developer 1's account. It cannot be in developer 2's account. This is also true of CA certificates. And that makes it very difficult to move devices around between accounts. So across regions, right, you can have it in the same account, in a different account, that's all fine. But within a region, it has to be unique on that single account. You can transfer them, though. If it's in developer 1's account, they can say, I'm going to push that over to developer 2's account. You can't pull. You have to know the account that it's in. So if developer 2 tries to connect the robot and it says, sorry, I can't do that, he or she can't say, pull it from whatever account it's in and transfer it to me. They have to go and find out what other developer has that robot registered. So given those constraints, you need some way of provisioning devices that's going to allow you to transfer them between developers and between test accounts, right? Because one option is to have separate certs and CAs for every dev account. So each device has a big store of certs on it, and when they say connect to developer 1's account, it goes and it looks up that and uses that cert. That's one option. Another option is to have sort of a single initial point of contact. So when you say connect to developer 1's account, it goes to this initial point of contact, which may be your prod account. It could be a special one that's just for this. And that will register there with that single cert. And then that account will push the device's cert over to the appropriate place. So those are two options. I don't think either one is better than the other. It sort of just depends on what your preference is. The final piece here, I just want to talk a little bit, get up on my soapbox about serverless ops, because I think it's very important to understand what's required when you go fully serverless as we have. And the answer is it's not no ops, right? Sometimes that term gets thrown around and it's wrong. It's not just misleading, it's wrong. You still need all of the things that you have traditionally needed. You want your infrastructure as code, whether that's in CloudFormation, or Terraform or any other system that you're using. You want build artifacts, right? When that Lambda code gets packaged up, you want it left in S3 so that you can see what was put up there. Then you want observability, logging, and auditing. And some of this is helped, right? You can just print in Lambda and that goes to CloudWatch logs. At the same time, a lot is hidden from you. If something in Lambda is not going as it should, you may not see it. You may just see the results downstream, right? So you have to figure out how to monitor an instrument to get the same metrics that you would be able to get if you were running your own infrastructure. So to sum up this section, I talked a little bit about iRobot's place in the smart home and where we see that going. Covered that when you have non-subscription cloud services in IoT, that means you end up being cost sensitive. We were able to skip undifferentiated heavy lifting with serverless. And going all in on that meant that we had to, figure out our own patterns, but it also meant that we were able to bring that system about faster than we would have otherwise. Talked about a few patterns: direct resource access between services, full red-black deployments as a strategy, using service discovery with a well-known endpoint for switching between deployments, and using CloudFront to deploy those well-known services. And then a little bit about patterns, account structure, and serverless ops. So to wrap up here, I'd like Wally to come back.
Thank you so much, Ben. It's always great hearing customers and hear about customers doing the...
I'd also like to make it clear that we could not have done this without Wally. Like, he was a huge help, and he knows more about, I think, both serverless and IoT than anybody else.
Great. So,
yeah.
thank you so much. So in summary, I know we talked about a lot of topics. A few key points. Think about those goals of your IoT architecture. You know, all these technologies and complex patterns boil down to fault tolerance, resilience, security, agility, visibility. So keep those in mind as you build your system. Think about the benefits of serverless IoT that we talked about being to remove the undifferentiated heavy lifting. And remember the blueprint about state management, fast pipelines, and IoT operations. So thank you so much. We will do a Q&A after this, but if you're not able to stay, definitely do the evaluations. We want to hear feedback. We want to hear what you really liked about the session, ways we can improve. And there are other sessions happening throughout the day. So there's some great IoT and serverless sessions coming up. So we definitely want you to check those out. So opening the floor for questions, and thank you so much again.